Well, welcome back, everyone, so far. We've got just under a minute. I definitely feel the going from Wednesday to Thursday being kind of tough sometimes for a really late night class. So appreciate all of your work ethics, making it in. I've always tried to get an answer from the administration on why we don't schedule on Friday. I never got a straight answer on that. Pocatello doesn't have a problem with Friday classes, but up here, everyone wants to take it off for some reason. And they've tried to schedule classes on Fridays, but people tend to not register for those classes. Even if they're like Monday, Wednesday, Friday, they're just not popular for some reason. Aside from that, welcome back, everyone. We are just about through all of our chapter 5, looking into the last section, 5.4. We opened it, but we were mostly just talking at it. We didn't make any big progress working through the material. On the new quiz, I decided to actually go for the quiz 5 to be on section 5.4. I felt like we have a high chance to get through the major content to support that quiz. So this quiz is a little bit special then. This one is going to require the TI-84 Plus calculator. And these two buttons with the highlighting here are going to be the major buttons we hit to get started on it. So we have quiz 4 due today. This one's on the box plots. Quiz 5 will be a week away and just kind of a normal week so far, finishing out week 6. Any questions at all, folks, to start us out today? Okay, let's jump back in then. Here's where we left off. We looked at the formula for this curve right here. We mentioned it's not a formula to memorize. This is just for the full disclosure. There's a real mathematical object that defines these kind of curves. We also put down the formula just for the sake of, it's good to see how does this plot actually look if we make a computer plot it. We could plot it in our TI-84 Plus calculator, but that's extremely tedious to put in. So instead, this is probably the one time we're going to use Desmos to illustrate a graph. So example 1 is not a real repeat kind of example on any kind of quiz or exam. Really, it's just us trying to get an intuitive feel for what the normal distribution looks like, what happens when we move around these two parameters, the value sigma, the value mu, where that's the mean of the population, and sigma is the standard deviation of the population. Well, mu is going to always deal with the center. It's a location parameter. Sigma is going to deal with the spread. It's how things are spread out. And if we start changing things, then this curve is going to move. But all we're doing is sketching real fast here. So one thing I should put in this right away is that this is supposed to be mu. I just couldn't find a way to make that actually work in Desmos, except sigma, but not mu for some random reason. But here's what it looks like. It's about like the graphs that we were looking at in the last section. If you're beyond 3 standard deviations, the curve is extremely close to the horizontal axis. But observe, you can go to a random spot. It will never actually hit the horizontal axis. You just have to zoom in a lot to actually see that separation actually come into play. So it's an interesting formula. Trouble zooming in that far as you have to zoom back out. But the key takeaway is this is what it would look like if you put it into a graphing software. So here's our first screen grab. Another thing that's interesting about these is you might have wondered, why is the vertical axis never shown here? This is a graph. It would go on the XY axis like we see here. We'll get some feel for why that is. It turns out the vertical axis numbers change quite a bit depending on the problem, and they're not as informative as we'd like them to be. The major thing that we want is the percent of area in regions under this curve. So this one, where mu is 0, sigma is 1, this is the N 0, 1 distribution, sometimes referred to as the standard, normal distribution. So let's try out another one. We're changing from mu is 0 to mu is -2, but this is the value of mu on the last one. Mu is right exactly at 0. It's kind of awkward to point out with the vertical axis there. So if this is a location parameter, just like y bar would have been called a location statistic, all it should be doing is taking this peak and moving it off to -2. So let's take a look into that. Let me try to get things to fit a little bit better. M is the mu here. Oh, I don't want to move it too much. There we go. M is the mu that we're thinking of. So if we move it to -2, it does precisely what we should have expected. This is the new location, now centered at -2. The shape of the curve is entirely the same. It's just changing where the center was. So here's one change, another normal distribution. And now we would call this one the n, -2, 1. It's weird how that went black and then blue. -2, 1 distribution. Recall when we say -2, we're referring to the value of mu. And when we say 1, we're referring to the value of sigma. Just to paraphrase, the normal curve centered at -2, standard deviation 1. So changing the value of mu is not that exciting, just the whole curve moves in exactly that shape. It gets kind of wild when you start to do this. We're going to change from sigma equals 1 to sigma equals 10. This is sometimes called the spread parameter, or it could be called a shape parameter at the same time, because it's going to drastically affect the shape of this thing. So this is also called a shape parameter. So it's going to affect how spread out things are. If we go from 1 to 10, either the curve is going to compress or it's going to stretch out. That's the only way it's going to affect its shape. And let's see what it should do. First, any predictions? Would you expect if actually it's set to 0, so let's bring this back to 0. Now next, we go from 1 to 10, what would you expect to happen? Would you say it compresses or it stretches out? I would agree with you. This is saying how spread out it is with a standard deviation of 1. This is saying it's 10 times as spread out. The spread parameter is increased by times 10. Spreading out means it's going to widen out or flatten out, like you said. So let's do that. Let's increase this up to 10. And here's our normal curve. I guess that's the maximum. Looks like just a silly line. And now the vertical axis doesn't seem to be too informative at all. And it makes it seem like this was a lie, right? We drew this no matter how big our standard deviation got in the last problems. But the trouble with why it looks so weird all of a sudden is -3 is just not really compatible with the graph if you have a standard deviation of 10. We need to change up our axes a lot. So we should go from, how about 3 standard deviations to the left would be -30. Let's go for maybe -40. 3 standard deviations to the right, or 4 deviations to the right, would be +40. And this is what it looks like. Not a big improvement, right? But this is not a shape we would have ever drawn in the last section. The trouble is the vertical axis is now just a little bit off. So let's change this for the y-axis, go to maybe -0.2, just to give some breathing room going in that direction. If that's from 0.5, how about 0.2 again? Maybe 0.1. Let's tinker with it a little bit. That was starting to look okay. -0.02. That looks like the same exact curve. Once you just tinker with this a little bit, looks like that one there. And this is an explanation already of why when we go to draw the normal curve, we're always basically drawing it to look exactly the same. We just choose the units going this way to make that happen. And we, in fact, never even put in the vertical axis. Notice how much has changed. It went from 0.5 to 0.05. That's just because the area got so massively spread out with that new deviation. So that's our new picture. And we would call this one the N, 0, 10 distribution. Or just using ordinary words, the normal curve with mean set to 0, standard deviation set to 10. Well, any questions at all, folks, getting through that one? Okay, I think one more just for the sake of seeing what happens. If we do the opposite thing and shrink way down, divide this by, say, 100, this curve is going to compress in by a great deal. So it'll look like this. Change this to a 0.1. And it looks like just a spike now. That's kind of weird and kind of inconvenient. We would never draw a curve that looks like that. And that spike gets more dramatic the more we put in numbers. At some point, the calculator just sort of breaks. There is a standard deviation where that's valid and a normal curve for that, but it really can't plot it too well any longer at that point. So here's our 0.1. And like before, it is the right curve, except we're going too far to the left this time, too far to the right, and we can fix that. Just on the x-axis, go to, if the standard deviation is 0.1, go to negative 0.4 for about the same picture as before, positive 0.4 going that way, and all of our area is like somewhere up there. We can fix the vertical direction just by going, how about, just delete that whole number and see what works here. I'll go with the calculator suggestion. Let's go with, how about 5 or something like that. Let's drag this up. So the view window I gave it a taller hump there. You may get more round there. That's just choosing, again, different values on the y-axis. Whatever y-axis scale we put on this is going to affect the shape entirely. It still has those same exact features as before, just a different standard deviation. So here's our last one. And the big takeaway with all of this is when we go to draw those normal curves, they'll always look the same. The vertical axis, there's a reason we don't put it in. It's not as informative as we would like. It's pretty interesting how it changes, and it changes very, very drastically as well, according to the standard deviation. The biggest thing that we want from this curve is where it's centered, how spread out it is by the standard deviation, and the percent areas under it. And that's what the calculator over here is going to assist us with. So that was just meant to give us a visual to try to demystify these kinds of graphics and what all that is saying. We're just playing around with that curve according to whatever the statistics are in the problem. So like before, this one would have been the N, 0.1 distribution, where that's always the value for mu, and that's always the value for sigma. Well, any questions, folks, with that quick graphing calculator work there? Okay, the goal with all this kind of stuff is this calculator can feel like a black box where you're just throwing in information. It's going to spit out a percentage, and you have to judge, is this percentage right? Did I put in the information correctly into the calculator? And sometimes that can be really hard to do if you don't have a good picture. The pictures that we're going to draw are going to be pretty basic, but it's going to capture all the information that we will need to organize what goes into the calculator itself. So let's start off those problems very next. Here's how they go. This one's kind of a simplistic context, so it's not too busy while we're learning something new. It's talking about arsenic, a deadly compound. Arsenic is a compound naturally occurring in very low concentrations, but if you dig a well, you should have it checked out just in case. Arsenic blood concentrations in healthy individuals, so people like you and me, can be modeled with a normal distribution with mean 3.2. That's a confusing symbol. That's for micrograms per deciliter of your blood. At a standard deviation, 1.5 micrograms per deciliter of blood. And just to make sure I'm on the right track with that, let's check that out. Mu as a unit, let's take a look into that. That's probably, yeah, that's more on the right track. No, not quite. SI units is what we want. Mu in units is 10 to the power of 6, 1 millionth of, well, anything. So that's what we would mean by a microgram, 10 to the power of -6. So per the 1 liter of your blood, there'd be 3.2 times 10 power -6 compounds of arsenic for the mean and 1.5 for the standard deviation. It's unfortunate to see mu used twice, but in this context, we just mean a specific kind of unit. So part A just says state the values of the parameters. One parameter is mu, and that's just referring to the mean right here. 3.2 micrograms, that's kind of hard to look at, written mu twice, per deciliter. The other parameter is sigma, which came from here when they indicate the standard deviation, 1.5 micrograms per deciliter. I guess one way to avoid saying mu twice is you could just write out that the symbol mu is micrograms. More writing, but maybe more clarity if you prefer to go that direction. Or might as well just say it all, 10 to the power of -6 grams. So those are the two parameters used in the model. And now we're ready to start off the problem in part B. This one is not a 68, 95, 99.7 rule. In fact, none of these are. Same with the quiz. And that's why we're going to start relying on the calculator over here heavily to get through these problems. Any questions at all, folks? Putting down the parameter values? Okay, because this is a major calculator operation, and this is our first time doing it, we'll indicate a sequence of steps. So step 1, press these 2 buttons. So on our calculator, the major buttons we'll hit, like we mentioned at the start of class, are going to be first hit the second button, then hit the distribution button. Oftentimes I'll just say second vars because that's the name on the button, but you're really trying to hit the thing in blue called distributions, as in the normal distribution. So press those 2 buttons in this order. I guess the order is important as well. Do this first. Do that one second on your calculator. Okay, let's try to make them not too gigantic so it doesn't get too busy. So that's the first thing you would do if you're putting all the information to the calculator as you see it. So let me hit second vars. And this is where it gets pretty vague. There's a lot of options here. It's kind of overwhelming. The good news is we're only using 1 or 2 options, option 2 or option 3. So part of the goal of these notes is to say when you're using one versus the other. It turns out for us, when this problem says what percent, that's the dead giveaway right there. That tells us to use option 2, normal CDF. So use 2 normal CDF, and that's the right option to use. So with option 2 highlighted right here, just hit enter right away. And this is where it gets a little bit vague. Your calculator might go -1E99. Let's say what that means. -1E99 is a calculator way of saying -10 to the 99th power. It's the largest negative number supported in this calculator's architecture. And we need to put a number in for all these different things. Mu and sigma is kind of a giveaway, right? It prints a mu and a sigma. But to really know what else goes in here, this is where we'd want to start to draw a picture. It asked, what percent of healthy individuals have more than 7 micrograms per deciliter arsenic blood concentration? Include a graph I wouldn't dock you on points if you did include a graph, but I put this in pretty much all of my problems on quizzes and exams because this is a good way for me to grade on partial credit. Again, the calculator is like a black box. It's going to give a percent out, and that number, if it's not the right number, it might be really vague to me how you got it. I might not have a basis for partial credit unless there's something on paper showing me the process that led you to it. So here's my quick and fast normal distribution. Not in the like in the last section, I just want two pieces of information. This is n 3.2, 1.5. So this gives us the mu and sigma value. It's often a good idea to put the center in here just to get everything oriented. And now let's read the question again. What percent of healthy individuals have more than 7 micrograms per deciliter arsenic blood concentration? So if you have the time to write this in, we can say that this is arsenic. Did I even spell that right? Okay, arsenic blood concentration. I'll just abbreviate that to CONCEN. I ran out of space there. So 3.2 is here, and the standard deviation is 1.5. 7 is probably pretty far out there. I'm not trying to place it exactly, but just in the right relative position to 3.2. So this is what the picture would look like so far. And the picture tells us what's going in the calculator. Normal CDF says the cumulative distribution function, but when it says cumulative, what you're accumulating is the area that's shaded right here. The way we get that area is this number right here is the lower bound. That's what the lower is referring to. What cuts off your area? It's the lower value of 7 coming from this part of the question. When it said more than, that means we shade to the right. So that's what we did with the shading here, kind of in bold. But it didn't say between 7 and 15. If it did, we would have had an upper bound of 15. If it just says strictly more than, that implies input 2, the upper, equals 10 to the power 99. We put in just the largest supported number in the calculator because that area goes to the right forever. Maybe if you put 1,000, you're going to get the same number. But you know, if the mean is like 1,000, that might not be good enough. If the mean is, say, 1,500 pounds, maybe you have to put in 20,000. If my mean is something like 30,000 gallons, maybe you have to put in an upper bound, rather, of 100,000. That's best to just put in 10 power 99. It's the fastest thing that you can type in. It's the thing that's always going to work for the upper bound. That's much like how this was the largest negative number possible. So that's input 1, 7. That's input 2, the upper. And this would be inputs 3 and inputs 4 in that order. Okay, so we're about to put it in. One thing I should ask the class, though, is I'm using just the classic TI-84 Plus, and there's other models. Some people might have the TI-84 Plus CE edition or Silver edition. You might have a nice display here rather than this one, which is kind of a basic calculator display. Things could look a little bit differently from you, and you might have a TI-83. Anyone happen to have a TI-83? I should ask first. Okay, so if everyone has a TI-84, that does simplify things a little bit. If you do have a TI-83 and you're maybe watching on a video later on, don't hesitate to reach out. I'm happy to show how that goes as well. Now, if your screen looks about like this, we're in good business. But if you bought an old TI-84 model from about like 15 years ago, you might not see this screen. You might see something else. Does anyone not see that screen? Okay, we're in luck today. Other classes, this goes a lot differently. So if you see all this information, just plug it in the order that we listed these out. The lower bound is 7 because we want more than 7 micrograms per deciliter. That means it doesn't stop. So we go 10. The power button is the up arrow right here. So go 10, up arrow, 99. So in the calculator, it really looks like this. 10 power 99 is 10, up arrow, 99 in that kind of way. So that's the largest supported positive number. You update the mean to 3.2, standard deviation to 1.5. And now because there's a picture, you should never get something like 60%, right? That would be so far off. That's a tiny percentage. In fact, 50% would have been if we put in 3.2 and go to the right. It would be exactly dead on 50%. So the fact that 7 is clear out there, we're expecting something really small. At this point, you just hit enter a bunch of times. It pastes something into the calculation field here, hit enter again, and it does the computation. Here's where it's also tricky. We want a percent. So you have to take this number and multiply it times 100, because we could lose credit in MyLab statistics. That's really annoying. So the number above is the probability. It's just fine on a quiz and exam. I would accept that number. MyLab statistics is hyper specific when it asks for a percent. You have to multiply it by 100. And I set to round to 4 decimal places, which is kind of extreme, but let's follow that to the letter. We'll say the answer is 0.5649%. So less than 1%, barely over a 0.5% of the healthy population of humans have a blood arsenic concentration more than 7 micrograms per deciliter. So that's a pretty unusual event. Probably no one in this room. We would have to look into rooms of size like hundreds of people to have a chance of finding one person. But the thing about probabilities and percentages are that also rare events also occur. There is a chance that someone in this room has blood arsenic concentration more than 7 micrograms per deciliter. It's just a very low chance. That would be a rare event. Well, I forgot I'm doing a step-by-step guide, so let's backtrack this once again, the calculator. The way I did this was I went second bars, then step 2 should say, hit enter on option 2. Normal CDF should look just like that. So your window looks like this on step 2. Then step 3, import the information. So your window on step 3 should look like this. And this is a cool feature already. It remembers what you put in. So when if we do a related question on the same model, we don't have to change those. If we use a different function, say 3 inverse norm, then we will have to change that one. It probably doesn't have that anything stored that we need. But this is what the step 3 looks like. Step 4 is a common thing we do once everything is put in the right order. Hit enter a bunch of times. So once you're down here on paste, enter, enter, and enter, and that gives you this. Let me go back to second bars just to show that again in a cleaner display. This is what you should get for your output to this kind of problem. So as a step-by-step guide, this is what it would look like. And maybe one additional thing we should say. Then multiply by 100, just because instructions are specifically asking for a percentage. So that's the process. Less tedious than the 68, 95, 99.7 rule, because we didn't have to put in tons of information and percentages. And it's also massively more flexible because the questions don't have to line up with the exact standard deviations anymore. But any last questions, folks, on getting through our first one? Yeah. Just for this one, yeah, that's what's gonna make this one really tricky. So if we change it and said had less than 7 micrograms per deciliter, we would have shaded on this end and used the negative 10 power 99 instead, which would have looked like this in the calculator. So that's why there's several questions to run through. There's actually a lot of different scenarios just to get a feel for these. So yeah, thanks for asking about that. Depending on the problem, our upper and lower can change quite a lot. Other questions so far? Okay, but this is the pretty much the new technique that we're looking into. Our first big calculator thing was just computing statistics, and this is our second major use of the calculator. So let's try it all over again on a whole new scenario. Because all this stuff is still pretty new, let's keep on doing this step-by-step guide. We won't do this on every single problem, but on the first example, I think it makes a lot of sense. Part C asks once again, what percent? That is a huge dead giveaway. Use option 2, normal, CDF. So we'll use that function again. But let's read into the question. We're asking this time, what percent of healthy individuals have less than 3 micrograms per deciliter arsenic blood concentration? So let's draw the graph for this one. Try to make it a little bit bigger this time so we can really see how things go together. I want to just copy in 3.2, 1.5. So this is the N 3.2. 1.5 distribution. So that's the mean, goes right here. And I'll call this just briefly arsenic concentration. That's definitely extra. That takes some time to do, but it's helpful the first time just reminding us of the context. We're asked what percent of healthy individuals have less than 3 micrograms per deciliter blood arsenic concentration. Well, first thing we want to do is put in the number 3 somewhere on here. But notice this time 3 is close to 3.2 because 1.5 to the left would be here. That's subtracting 1.5 from 3.2. So my 3 is actually pretty close. We're not trying to place it perfectly once again, just get it close to where you think it should be relative to the standard deviation. And when it says have less than, this is now telling us to shade to the left. So that 3 we put down, it causes a boundary. That boundary cuts off the area. Shading to the left, I'll do it kind of a lazy way like this. Looks like this time. And now the inputs are different. Well, the step 1 here is still the same, so let's maybe save some time and just copy this in. Geez, that's harder to do than I thought. Okay, here's step 1 once again. You still just hit second and bars, go back in here, because we're finding a percentage, the area percent under the curve to the left of 3. We go to normal CDF once again. So that's our step 2. Use normal CDF. Then we hit enter there. There we go, finally. We have the prior information that we put in just on the last problem, but the organization is different this time. Like the question you were asking about the last one, we're not going to use 10 power 99 on this one. The situation's different. Upper means the upper bound. That's the upper bound that cuts off the area right here. So this time input 1 for lower, Because this area is extending to the left forever, it didn't say between two values, it just says less than 3 micrograms per deciliter. Lower is -10 power 99 in the calculator. 3 is the upper value. And inputs 3, inputs 4 are always in the same order, but the calculator helps out definitely with that one by printing those symbols. So here's how the lower would go. Recall the thing that's nasty about the calculator. If you go like this, that's automatically going to give us an error, even if everything else looks right. It's because I didn't put in the negative sign, I put a subtraction symbol. So let's show what that error would look like. Hit enter through this. You'll say syntax error. And a good strategy whenever that comes up is down arrow to the go-to. If you hit enter on that, it'll tell you that was the problem right there. Well, we still have to fix it. So go to second, vars, normal CDF option 2. There's the problem right in that spot. You have to literally use that negative sign. Again, that's really annoying sometimes. Go -10, go up arrow for the exponent, and 99. Now that was the largest negative supported number in the calculator. And again, you could just go -1 and a bunch of zeros. But depending on the mean, you might not have put in enough zeros. Sometimes our means are huge, depending on the context. So this is just the safest approach that always works for a shade to the left type of problem. So with all that set up, that's our step 3. Import the information from the graph, and here it is. And step 4, hit enter a bunch of times is the official approach. So here it goes. Enter, enter, and that's the value we want. Notice if this 3 was right at 3.2, area to the left is exactly 50%. So the fact that it's just a little bit less than 50%, that feels accurate. It seems like it's in the right ballpark. All we need to do is multiply it by 100. So we'll bake that into this step. Enter a bunch of times, multiply by 100, and this is the answer we're going for. So we got it, folks. The answer on this one is 44 to 4 decimal places. I kind of went wild on the decimal places. Usually 2 decimal places would make more sense, I'd say. 0.6965 upon rounding %. So it's telling us if we just grab a random person and we suspect they're healthy, they haven't been poisoned by arsenic or anything crazy is going on with them, then about 44.7% of the time, their blood arsenic is going to be below 3 micrograms per deciliter of blood. So that's the wrap up of this problem. Again, there are assumptions. There's assumptions of is how accurate is the normal model? How accurate are the parameters, the mean and the standard deviation? All of those things are accurate. At least we weren't using the 68 to 99, 95, 99.7 rule because that's yet another approximation. The calculator is actually very, very accurate at doing this kind of area finding. Well, any questions, folks, on this problem so far? Okay, really our notes are turning into just kind of a big cheat sheet. We're going to look into all the scenarios that can come up on any quiz situation, any exam situation. So next one, well, this one is a little bit different out of nowhere. Let's be careful with this one. It asks not about a percentage anymore. It provided a percentage this time. What blood arsenic concentrations describe the 25% of blood arsenic concentration, that should probably be plural, concentrations in healthy individuals? Include a graph run to 2 decimal places. And this time, when we organize our thoughts on what function we should use, the fact that a percentage is given is the dead giveaway that we want to use. Option 3, inverse norm function. It's kind of like what we did with the 68, 95, 99.7 rule in section 5.3. Some of those problems were kind of backwards. They gave us a percentage, and we had to find the value on the horizontal axis that corresponded to that right percentage. Well, we can do this in a little bit more accurate way. Well, in fact, a lot more accurate way. But to see what goes into the calculator, the picture is still really important. So here's the basic curve. This is n, and I've already forgotten 3.2, 1.5, I think. Yeah. And 3.2, 1.5. So we have a center of 3.2 here. Now it says, what blood arsenic concentration describes the 25% of lowest blood arsenic concentrations? Lowest right here would say shade to the left, once again on this problem. And we'll see a shade to the right problem on our next example we're looking into. But here's what's weird. Shade to the left of where? Well, you just have to use your eye. We're trying to cut off the lower 25%. So to my eye, lower 25% might look about like this. It's not perfect. I might be a little bit off. Maybe that's 20%, and you'd move it to the right a little bit, but just get it in the right ballpark. In other words, we wouldn't put it way out here. That's more like lower 75% if we shade to the left there. So to me, this might be about right. And then there's some unknown value here. This is, once again, blood, arsenic, concentration. Let's put this as an X. Kind of reminds us that this is actually really equation solving. We're provided the percentage, 25%. So we'll say here, for input 1, I believe this is called area, but let's double check that before we get too far ahead of ourselves. Go second vars once again to start it off. Go down to inverse norm, option 3. And yeah, it's going to be called area, so that's good. Notice the steps are different already, so let's start putting in these new steps. Let me go backwards a step as well. So first thing is we hit second vars to go here. Guess that's this first graph right here. Step 1. That is not step 1, darn it. Press these 2 buttons. Sorry, 1 second, struggling with the screen grab here. Certain I copied it this time. Let's see if it works. There we go, 3, 2 buttons. Okay, then step 2. Only because a percent came in the problem and the value X, the actual blood arsenic concentration, is unknown, if they give you the percent, we wouldn't use normal CDF because that's what gives us the percent and we have one. So we go down to option 3, use inverse norm. So your calculator should look like this right before you hit enter. So to enter there, and that's where the inputs go in. So we have an area. The area is going to be whatever this number was given to be. Area equals 25%. which is the same as the area that we were shading in to the left. That was meant to be 25% of the area as well. However, some people's calculators might look a little bit different. Depending on the model you get, you might have something that says left tail, center, and right tail. You're seeing that as well? Awesome. My calculator, or if you spent the least amount of money possible, you have something similar, would just look like this. My calculator will only give the left tail, so your calculator is probably the same as well. As per the picture we drew, you'd select left tail on your calculator as well. I don't seem to have that screenshot of what it would look like. So let me know if you're getting a different number on your calculator. So another thing that's weird here, that area has to be a decimal number, 0.25. So this is what actually goes into the calculator. Let me rewrite this number here. So input 1 for area as a decimal is that number there, 0.25. Turns out the exact area under this curve is 1. It doesn't matter what the mean and standard deviation is, it's exactly 1 for every normal model that we plotted and drew. That's a weird fact already onto itself. But the takeaway is take your percentage, convert it to a decimal number, and this is what should go into the calculator. From then on out, we import the model parameters. Mean is 3.2. Standard deviation is 1.5. And this should do the job for us. So let's convey our step 3 by saying import the diagram information, convert the percentage to a decimal. So whatever we have here, just move it 2 spots to the left and you'll have the right decimal number. So it should look like this right at this step before you do the main step of hitting enter a bunch of times. So let's see what this looks like. Step 4, mash the enter key. So that's just entering is going to take you down all the options. You'll paste the function into the computation screen, and this is what we get. I'm getting about 2.1 micrograms per deciliter blood arsenic concentration. Is that what folks are all getting so far? Yeah. Yeah. Exactly, yeah. So if we shade to the left, you'd be selecting the left tail on your calculator. Absolutely. And for those calculator models, let's put that on the note as well. So for some models, unfortunate that this is only in some models, select left tail. Does it say it that way, left tail, or does it just say left? It does say left tail. Awesome. I need to look at a picture of that one time. I'll just Google that at some point. So select left tail if you have a slightly more advanced display, kind of like maybe like a smartphone display. That'd be the giveaway. And then this is the number that should come up. Well, we got it, folks. That's using the TI-84 calculator. This problem is tricky because, again, it's a reverse type of problem. The end answer to this is x equals, you don't necessarily have to write the x equals, but if you're conveying it from the graph, it'd be x equals, let's see, to 2 decimal places, 2.19 micrograms per deciliter. Let me double check. Yeah, that would have rounded up to a 9. So that thing is the whole answer. You didn't need the x equals part, but we should often actually complete the diagram. Come back down here and put in the value for x, 2.19, because this is a sanity check or a smell test. That should have been less than 3.2. So if I got a 4.7, I'm going to know right away something just isn't right on my diagram. And, for 25% of the area, it's not crazy far away. 7 here, way up here, was when we had less than 1% of the area. That's when it gets really far away. So everything looks like it's in about the right ballpark, and that's a good way to catch simple mistakes on these kind of problems. If this was a real exam question, even on a final exam, if you put down on paper 2.19, it is for full credit, but it's kind of a gamble in a certain sense. If you have the time on the final exam, drawing this out is all partial credit. So if you got this number completely wrong, maybe you put in 15.73, and this is a 5-point problem, you might lose a couple points because something did go wrong with the calculator. That is part of the objective. But all of this would be considered partial credit. You'd still get 3 points out of the 5. I would assume that maybe you just got things backwards. Maybe you put in 75% instead of the 25%, but you're thinking along the right lines. So if you're really certain you've got the right value, this qualifies for full credit on quizzes and exams. But anything additional is basically insurance for partial credit purposes. Any last questions at all, folks, getting through these problems? Okay, so the diagram really helps out importing all this information to the calculator. If you do this a lot, you might not need the diagram, but it's still a great paper trail for the notes and partial credit like we mentioned. So let's try this one more time. This will be our final question for the night. And then our quiz number 5 is going to be similar to these two. Let's take a look at it before we go into the next problem, just kind of a cognitive break. Quiz number 5, I put in a little bit more context to make it interesting and seem meaningful. This one is about being screened for your blood glucose level and possibly being categorized as having pre-diabetes pre-diabetes. So it tells us in a healthy non-diabetic population, fasting blood glucose are known to be approximately normal. And we call this Idaho Falls region. It's made up data, but it makes it seem personal now. Let's assume, for the sake of a math problem, in Idaho Falls, the average fasting blood glucose is this value. So that's the parameter mu. Standard deviation in this value is sigma. And according to medical guidelines, person is categorized as having pre-diabetes if your fasting blood glucose is between 100 to 125. Not medical advice. This is just a random math problem. So we'll do the same kind of thing. State the value of the parameter, do problems like we did before, including a graph is for the sake of partial credit. And that's pretty much what all this is about. This is the tricky one because when it says 10% worst cases, that's the inverse norm problem. And worse in this case means high blood glucose, so on the upper end. And that's a problem we're about to solve on this one. Worst cases, depending on how you feel about snow, is also a percentage on the upper end. So we're switching up this problem, putting the percentage on the right tail this time. So that quiz is pretty similar to the problems we're seeing here. And here's the context. So Idaho does get a lot of snow, but Rochester, New York averages 21.9 inches of snow in December alone. And that's pretty impressive as a parameter value. The distribution of snowfall in this place in New York is normal. So we mean more normally distributed. And it has a standard deviation of 6.5 inches, which is huge. So they not only get dumped on by snow out there, but there's a huge amount of variation. They'll have some calm years and they'll have like snow apocalypse years. Just depends. That's a big deviation. So what it says to state the values of the parameters, anyone spotted what the value for mu should be? Yeah, absolutely. The moment they say mean or average, that's the parameter value they're specifying in this. There's no sample data whatsoever. This isn't a study where they took a sample of months of December across the years. Looks like they're just giving us the best estimate for what the climate looks like now in Rochester, New York. Likewise, this one's kind of a giveaway. When it says standard deviation, That's the referring to the sigma value, 6.5. Units on both are inches. Good idea to put them in, not required for credit, but can help with context. Okay, so now we're running through the questions. The first question is a what percent question. So this indicates directly by the format of the problem, this is a normal CDF problem. So the question asks, what is the percent chance? This is basically a probability question. Every one of them have been that Rochester will experience 10 inches of snowfall or less this year. So here's what the rough graph is going to look like for that question. Go to a normal curve. Give it a quick description. This is N21.9, comma 6.5. So that's our mu and sigma values we stated. But it's also inputs 3 and 4, the last inputs in the calculator. So 21.9 would go here. We have 10 inches. 10 inches is going to be to the left. And if I go 2 standard deviations, that's 13 values. 10 inches is probably somewhere right around here. Again, I'm not trying to nail it exactly, just get it in the right approximate region. I'll say that's where 10 inches is. It could help to have context here. This is inches of snow in Rochester, New York in the month of December, but we can really paraphrase it down so it's not tedious to write. Now that we placed it 10 inches, the question becomes, which way do we shade? Are we going left or right on this one?
Less.
Yeah, good call. From this right here, shade to the left. So our shading would look about like this. And this tells us what our next inputs are. Input 1 is the lower bound if we have one, but there is no lower bound. There's just an upper bound. That means the lower that we put in is -10 power 99. That's what we'll import into the calculator. Next input 2 is the upper bound. 10 inches is the upper bound because it's where the area stops. It's the upper fence in a certain sense, upper boundary. And this is enough to just go right to the calculator. So hit second and bars to call up your distributions. We're using the normal distribution and normal CDF because we're finding an area. Hit enter and just put in the new information. And hey, my calculator seems to have reset. If you see -1 E99, that works too, but I don't know how to type that usually. Oftentimes it's going to look like this. -10 power 99, but it does the same exact effect, either way you write it. So I could have just left it as the calculator showed. Go hit enter, put in 10 for the upper, hit enter, and inputs 21.9 for mu, and 6.5 for sigma. So at this point, we've got it. Let me know if you get something different. We're at the hit enter a bunch of times. We want to percent, and that's a little bit more reasonable. 2 decimal places is about right for a normal problem. So don't forget to go times 100. And to 2 decimal places, this would be 3.36 rounding up. So 3.36% of the time they have less than 10 inches. I wrote out a whole statement, and that's okay to do as well. The 3.36% is the whole answer to this. But sometimes just writing down the statement forces you to think, is that reasonable? Does it even make sense? And yeah, that does seem about right. They get a heavy amount of snow, and even though the standard deviation is large, even on our graph, that looks like a small value. So I would say that looks pretty accurate for the context and what we actually drew as well. So they're pretty fast problems once we get the hang of the calculator. We didn't put the step-by-step chart on this one. Did it make sense to everyone how to get that number? Okay,
This is how we, like that problem we did yesterday with the water.
exactly like that
This
one.
is how we would find out exactly like if it wasn't that deep or.
Yeah, exactly. We would have made 80 the lower bound, 10 power 99 the upper bound, and we'd have gotten a more reasonable answer. And I'm glad you mentioned that because just for the sake of taking a look into this, let's see what the more accurate answer would have been. The rule we used is an approximate one, and this is a pretty fast check for us. So I think it was, yeah, down here. It was part D on this question. So to just get a more accurate answer, let's see what happens. We have the model right here, N75 4.2, so hit second bars. Part D is asking what percent. So we're going to go normal CDF. But what we really wanted to ask is, what percent of the time are these batches of 500-gallon waters in violation? More than 80 parts per million. So that's going to be our lower bound, 80 there. Upper bound is going to be 10 power 99. So essentially what we did here, like you were mentioning, we added up those three percentages. What we would have done in our new section is just shaded to the right and put 80 down right there. Then we update the mean to 75, standard deviation to 4.2, and our approximate figure is 16% of the time they're in violation, and they're approximated twice. The rule is imprecise, and we didn't use the cutoff we wanted to, which is exactly 80. So here is the better answer to that question. It's way different, right? It's like 12%. So this one was really actually remarkably off of what we really wanted. So go times 100. Here it is as a percentage. And I guess that's the real nice value of having a better way to compute. This rule is just to get us thinking in terms of what the picture looks like. But for the sake of being more accurate, let's put this in the notes as well. This was highly inaccurate. Maybe it's not bad. We're going to scare the company and say 16% of the time you're in trouble. But in actuality, it was closer to 12%. So here, this is 11.69% of the time they are in violation. That sounds really stern. They're above 80 parts per million. Let's say that just to be specific, above 80 parts per million. So the TI-84 calculator, it's a crude tool. This was a chip that's like 30, 40 years old at this point, but it's still a really powerful computational device. Well, any other questions or comments so far? Forgot where it was. There we go. Okay, so let's try this out again on the next follow-up question. I know this one's a little bit new as well. Between 10 and 20 inches. We haven't done an in-between problem just yet. Like before, what percent means we're using the normal CDF once again. Normal CDF. And the picture looks like this time. And 21.9, 6.5. So blue here, green here for the mean and standard deviation. And now the figures go between 10 and 20 inches. So 10 inches was, again, pretty far to the left. 20 inches is getting really close to the mean. So there's 20. And this time we shade between. The shading goes like this. So shade between. And it means the inputs to the calculator are also different. This is low input 1, the lower bound. This is input 2, the upper bound. Then same inputs 3 and 4. But again, totally new scenario. Sometimes they're in between kind of questions like this one. This one looks like it's anywhere between, if I had to give a really rough ballpark, 30 to 40% would be my guess on this one. So let's go back to the calculator. Second bars, because it's a normal distribution window, and I missed. Let me try again. Now go back to the normal CDF, because we're finding a percentage. Lower bound this time is 10. Upper bound this time is 20. And this is the situation when there's no 10 power 99, either positive or negative. The values I did switch on the last problem, so let me correct those. 21.9, 6.5, and this should be what goes into the calculator. So hitting enter, and this is to 2 decimal places again. This would, oh, hang on. Before you go and round, it's always a good idea to multiply by 100 and then round. If I rounded right now, I would get the wrong percentage. Okay, so now round at this place. We're rounding to 2 decimal places of the percent. So this would round upwards to 35.15% of the time. So 35.15% of Decembers have between 10 and 20 inch snow fall. So we got it, folks. That's the end one on that one. We're down to the very last question. It's a worst case scenario kind of question. The major feature about this one is right where it says 1%, and it's also asking for what amount of snowfall. Those were the givens in all the rest of the questions. So this question is fully backwards. Let's put it on the next page here. This one is an inverse norm question. So if we go to fill out this one, here's what the graph would look like this time. For inverse norm, here's the new normal distribution. This one is kind of rough, but again, doesn't have to be perfect. It kind of looks pretty bad to my eye though, so let me kind of fix it. That's a little bit better looking. 21.9, 6.5, just to check parameters. And now this time when it says worst cases, I feel like this doesn't make a good exam problem. This is open to your interpretation. Some people like snow. Some people are snowboarders. Idaho is a great state for that. Some people are skiers. And worst snow for them is no snowfall, because then they don't get to go up in the mountains. But I think most people would interpret the worst in this case as being too much snow. You're now shoveling a lot of snow. I feel like as an exam question, I would need to be specific on that because it's somewhat open to interpretation this time. So worst cases means an excess of snow, too much snow. So we would shade to the right. Turns out the quiz question is just like this one. It's a shade to the right problem as well. You'll go 21.9. This would be input 2. This is input 3. And when we say 1% of worst cases, well, we're going to put in a value somewhere out here. I'll call it X again. And this is shading to the right. So that's the 1% right here. As a decimal, we move 2 spots to the left where that point is by the symbol. We get 0.01. And in some people's calculator, that's input 3. You'd have to select right tail if that's your calculator. However, in this calculator, it has a bit of a, not exactly a defect, but an extra challenge. You would not use this decimal number. It only operates on areas to the left. So 0.99 would be input one, area to the left. Now, on everyone's calculators, you could use 0.99. You just have to select the left tail. How did I get 0.99? This number here and this number here have to add up to exactly 1. But I feel like that's a lot of comments for now doing the computation in 20 seconds. We should come back to this problem when we're a little bit more fresh on Monday and show how it goes. So we'll look at this from scratch, how to put it together. But if you wanted to start the quiz early, I'm going to leave the notes in this format just to give you a guide on how it's going to go, because our quiz is also a worst case scenario like this one. But any last questions, folks, on getting through the setup at least? Okay, sorry for running over the minute on this one. It takes a little bit of time just to describe how all these kind of things go, but it's time well spent. When we come back on Monday, let me know if you feel like another problem would be helpful. I could put in a new problem on these notes. So you could send me an email before class, let me know after class today. And if anyone would like to see just an additional problem, I'll be happy to do so. Otherwise, on Monday, we'll restart this sketch and then fill out this problem in full. That means also the due date for MyLab statistics on section 5.4. I'm going to push the due date since we'll finish it officially when we come back. Its due date is really going to be, let's see here, the 13th of October. But have a great weekend, folks. We'll review this stuff when we come back. Here's this back for you. Thank you. Any questions?
Yeah, I have a couple questions. So for this one,
Yeah.
can you tell me if that's okay? I just want.
Yeah, I like this. Really, the major part of it would be that last sentence right there. Because you're talking about what you see in the box plot specifically. And I agree, that's a highly symmetric distribution. So that looks great.
Okay, and then I was also confused on how you like got those percentages yesterday and.
Oh, yeah.
Curve.
So those percentages, they turned out, it was like essentially a type of formula. It came from, so I get that going, the very top right up here. So this was like a given formula coming from the 68 95 99.7 rule. And we just broke it into segments like that.
Okay,
So one thing that we did calculate was the 0.15 on the either ends, but we basically took 100 minus 99.7 and then we divided it by 2.
okay,
So this would just be in a certain sense like the given information, much like a formula.
okay, perfect. Thank you.
Yeah, absolutely.
Here's that.
Oh, awesome, thanks.
Yeah.
Any questions?
Yeah, can I ask you to, because it's gonna freaking bother me?
Yeah, absolutely. Are you looking into that last problem?
Mm-hmm.
Okay, so area 0.1, right tail. Yeah, that looks like exactly how it should go.
Okay, and if I,
And you got 37 inches. And yeah, that looks right on the diagram. You're at the 1% worst case, 37 inches. Clear
okay,
out here away from 21.9 inches.
and so if I was to check it. Right, and then if I come over here and go to the left tail,
tail, yeah. That's the way we'd be happy to do it on our other more basic calculators. Yep,
and I get the same,
yeah.
okay,
So you could always, if you wanted to, just specifically use the left tail. But in your calculator, I think it's easier just if you shade to the right, just select right tail. It's gonna be more straightforward.
yeah.
But it's confusing because on our notes, we're gonna have to put that in for the other calculators.
Okay, it just, I was doing that sitting here, and I was like. It wasn't making sense to me why I got the same number for some reason.
Gotcha.
I was thinking, I don't know, I was just overthinking it, I think,
Yeah,
you know what I mean?
definitely. It's a new weird curve and now a whole different way of computing on it with those new functions.
Yeah,
So it's like everything is just, that's what statistics is like. 1 week, it's like everything you learned, it's now all totally different because we're in a new topic.
right. It's really not a problem.
Awesome, I'm glad to hear that.
I'm not the algebra guy, that shit,
Yeah,
like even when we did that, I mean, solving for X,
yeah, on those Z-scores, that's right.
yeah, that makes it a little, I don't know. This is a lot easier for me, I think I get lost a little sometimes in
Mhm.
writing the descriptions,
Yeah,
but,
I think you're doing a great job of getting the context in though, on those kind of problems.
well, I honestly am reviewing the notes when I do it, though,
Mhm.
does that make sense?
It does, yeah.
So like, I'm using the cheat sheets big time, for
Mhm.
what we've gone over. So it's
Awesome,
not like I'm completely just writing them blank.
yeah. But you know, that's what it's all for. I remember being a statistics student myself, like in 2005, and I felt the same way. It felt like the questions were so open-ended that anything I wrote down, it just felt like I was never matching up with what they really wanted. So you get over that kind of uncomfortable feeling after a while.
Yeah. Yeah, and I bet the more we do it,
Yeah,
so. Right on, man, well, thanks for all your help and have a good weekend.
you bet. You too. Try not to work too hard.
I will.